so what did we cover last time? Let's just recall. Recall what we were doing last time. So if we have a sample, x1 to xn, IID normal, so distributed like mean, mu, variance, sigma squared, okay? We want to know what we used to do, so the point estimator for mu is just x bar, so this is mu hat. Mu hat is an estimator, x bar. You take your samples, you add them up, you divide by n. That's the best you can do. But of course, we want to be able to say much more. We want confidence intervals now. Okay? So instead of a point estimator, now we want a confidence interval. Confidence interval. And the confidence interval is the observation that the probability that x bar minus mu divided by square root of sigma squared over n is bounded by some number is equal to the integral of that number. The integral of that over whatever I put here, the integral from minus that to that of the Gaussian density. So if I want that to be 1 minus alpha, like 95%, then what I should put here is z of not alpha, but alpha over 2, exactly as Zach said. Okay? So alpha over 2, because I'm taking a two-sided confidence interval, I want to forget alpha over 2 of the mass that's too high and alpha over 2 of the mass that's too low. In total, that gives me this. Right? Everyone's happy with the concept of confidence intervals? So this is saying a Gaussian normal. Here's my f of a Gaussian, e to the minus x squared over 2 with a constant 1 over root 2 pi. Here's z alpha over 2. This much and this much of the mass is what I want to exclude, and that amounts to alpha, which means the bulk is 1 minus alpha. So that's my 95% confidence interval. And if you unwrap this, that tells you that this is the probability that mu lies between x bar plus, what do we have here? Z alpha over 2 times sigma over root n. And the same thing with a minus sign. Z alpha over 2, sigma over root n. We're happy with this? So that's, if alpha is 0.5, then z is, what was it? Z of 0.025 is like 1.96. Do you remember these numbers? So if alpha here is 0.05, so this is 95% confidence interval, then it turns out that z of 0.025, you just, this book is 30 years old. We're going to talk a lot about modern statistical analysis, which this book unfortunately is not. So I'll tell you the techniques that people used to use, and I'll also tell you why they're really, really wrong today. So anyway, we'll get to that. So if you go about 2 standard deviations over square root of n away from whatever your empirical, the sample mean is, that's a good confidence interval. If you know, for some reason, if you know what sigma is. How could you know what sigma is and not know what mu is? Well, this is just a theoretical question. So this is if sigma is known, and if sigma is unknown, estimate by s squared, or estimate sigma squared by s squared. But then the distribution is something different. It's not a Gaussian, it's a t-distribution. I'm just reviewing what we did last time. The probability that x bar minus mu divided by square root of s squared divided by n is at most something. We want to be 1 minus alpha. This is a t-distribution with n minus 1 degrees of freedom. So if I just figure out how much a t-distribution with n minus 1 degrees of freedom contributes to a tail of size alpha over 2. That gives me a t confidence interval. And what we saw last time, so if you unwrap this, you get a very similar picture to this. It turns into, let's call this double star, that this probability is equal to the probability that mu lies between x bar and x bar minus the same thing. And what is that thing? It's t alpha over 2 n minus 1 times s over root n. And the same thing with a minus. That it will be equal to 1 minus alpha. Let me pause here. This was all review. Is everybody happy with what this says and how this is applied? So now you know exactly what to do to estimate mu, knowing nothing about your distribution other than assuming that it's normal. That's a big assumption. Who says your data is normal? But let's say your data is normal. Maybe there's some pre-packaging, normal is the right thing because of the central limit theorem. Whatever it was, whatever your distribution was, if you average, central limit theorem says if your average is sufficiently large, it should start looking normal. So we're going to assume that the samples themselves are IID normal. Here we know nothing. We don't know sigma. We don't know mu. This is purely a function of the x's. The x's come out. You compute s squared. You take the square root of that. You compute x bar squared. You compute this number, depending on how many n's you had, and what you want, if you want a 95% or a 99% confidence interval. And then this is exactly the calculation. Any questions? How many people are totally comfortable with this? They understand everything that's going on. Okay. I didn't see a whopping all the hands going up. Is there? Sakina? Will you tell me something? Does this make sense? Okay. Who else can I pick on? Are there any questions? Gates.
So like when you draw like a graph, why when you show the area, why does it start with
Why does it start with?
the right side?
When I draw a graph of the t distribution, so the t distributions, as a hand-drawn picture is going to look very similar, except it really goes like 1 plus x squared over n minus 1 to the minus n over 2 with a constant that I won't write down since I'll screw it up. So this one is decaying. This is for degree n minus 1 degrees of freedom. So, a hand-drawn picture, they look the same. The only thing about it is it's an even function. So that's the only place where I'm using the fact that I can capture both sides with one number. Is that your question? Did I answer your question?
So when you write T alpha,
Yes?
why does it start with the right side? Whenever it's
Oh, that's just what, okay, so Gates's question is, how come when you write T alpha, that means the right side? Well, it could also mean the left side, because of the symmetry. X goes to negative x, it's an even function. So just human beings at some point decided that that's the notation they wanted to use. There's nothing deep about this. So z alpha means the integral from z alpha to infinity of e to the minus x squared over 2, 1 over root 2 pi dx is equal to alpha. So that's just z alpha is this tail. You're saying why don't I call it z alpha this tail? It's the same. Yep. And same thing with the t's. Yeah. I don't know why I drew it on that side. It's the same thing. I guess I drew it on that side because our other example was a one-sided confidence interval instead of a two-sided confidence interval. And I was thinking of, if you're like an insurance company and mu is your expected payout from claims. Well, if you have to pay out too few claims, that's great, that's profit. You don't care about, that's not a catastrophic loss. This is a catastrophic loss. If you start paying out a whole lot more than you expected to, that's it, you're out of business. Company shuts down. Okay? So this is like, you know, Lehman Brothers or something. Right? I mean, it's not funny. People lost jobs and it was a problem. But yeah, so that, I guess that's why I was thinking about it in that example, but you're absolutely right that I mean, it's the same thing. There's no reason to draw it there. But I do want to bring to your attention this thing. So the textbooks say once n is at least 30, approximate t alpha over 2n by z alpha over 2. And I said, well, that's pretty close, but it's not that close. Let's actually look at how close it is, because we started doing the numerics. I think I can do this. Let's see. Let me show you the computer. Can you see the computer? So the point I want to make is that today it's so easy to do the numerics instantly without knowing anything. You don't have to be like a computer programmer to do these things. So let's go Wolfram alpha. I'm just going to Google Wolfram alpha. You can't see that. There it is. Wolfram alpha, let's say t distribution, let's say 30 degrees of freedom, really 29, but okay, wait, let's be precise. 29 degrees of freedom. Well, let's see what it'll tell me. Critical value of t. Here we go. Okay, there it is. Okay, you Googled this stuff. By the way, Gates, was it you who got me the numbers last time? Somebody was Googling the numbers. I don't know how you did it. Dylan, you were Googling them? All right.
That's also 10 degrees of freedom?
Right, I'm going to change this.
Yeah.
Okay, so let's do, let's just see this thing in action. So here's 30 degrees of freedom, or let me be precise, 29. The point I want to make is you should be precise today. There's no excuse when you're not doing lookup tables any longer to be doing imprecise things. Ernest?
Make sure you change the tails to 2.
Yes, yes, the tail is 0.25. Can you see this? I need to make this bigger. How do I zoom in? Here we
I
go.
think the significance
Because
stays
level
at
significance is
0.05, just the number of tails changes.
Yeah, got the number.
Number of tails, two-sided, two-tail value. Okay, submit. And this is the number we saw last time, 2.04.
Wait, should we say right tail?
I could say, okay, let's test if the software is doing what we think it's doing. If I say 0.25 and give me a one-sided tail.
Change the direction to right.
Oh, direction. Yes.
Everything to match.
Directions should tail the number. Okay. Admittedly, that's a bit redundant. Sorry. Yes, you should be sorry. It's the same number, 2.045. Okay? So if I am supposed to have, oh, now you can't see this. How do I get back to DocCam? If I'm supposed to have here, if I'm trying to give you, any day now, if I'm trying to give you a 95% confidence interval here, and I'm supposed to have a t-value of 0.45 or something. Okay, if I actually use 2.045, I will get a 95% confidence interval. And what the textbooks all tell you is instead of that, what you should do is use z. Now z we can also Google. Is this going to take forever? Let's do Wolfram alpha, normal distribution, and z value or something. Widget z-score calculation. No, I don't want to do that yet. We're coming up on that. Critical z value. Here we go. Okay, so it's going to give me, let's do the one-sided again. And it should be 1.96 exactly. Okay, so that's what we saw last time, 1.96. So if I use, I'm going to get better at flipping between the two. Or I should do them all at once, or leave one on the board. That's what I should do. I should leave one on the board, because this isn't instantaneous. So if I use 1.96 instead of 2.045, sure, they're asymptotically, they're not so far, right? They're both roughly of size 2. How bad is that? Well, let's see how bad that is if you're an insurance company and you're doing this approximation. Okay? So if instead of the true value, 2.045, I substitute an approximate value, 1.96, how far from a 95% confidence interval do I actually get? It's not going to be 95. What is it? So how would we answer that question? Well, all we have to know is what the cumulative distribution function, so again, Wolfram alpha, cumulative distribution function of a t distribution with 29 degrees of freedom students t distribution. Okay, let's just try Wolfram alpha. Just go to Wolfram alpha. Let's try it like this. Okay, so I want a t distribution cumulative. Yes, t distribution. Wait, cumulative. So here's the t distribution. I want to say with 29 degrees of freedom, 29 degrees of freedom, and at x equals 1.96, which is the incorrect value. First, let's check if it gives me the right value, 2.045, right? So 2.045 is the actual t value that I want, and there the value is 97.5. In other words, 2.5% is the error. Is everyone following this calculation? Let's do this on the board where you can see. So here's the t distribution. This is the t distribution. Okay? What I want to capture is 2.5% error. In other words, I want to capture 97.5% cumulative bulk. When I put in the correct t value, t alpha over 2, that's at 2.045, I recover what I'm supposed to recover, 97.5%. Now let's put in the incorrect value. Instead of 2.045, I'll put in 1.96, which is what we get from approximating a t distribution by a z distribution, by a Gaussian. So that's a little bit smaller. That's here. Z alpha over 2 is at 1.96. And instead of 2.5%, I get 97% cumulative. So this is 97%, which means z, which means this part of the density, this extra little bit, goes up to 3%. Does everybody see that? So what does that mean? Let's go back to the board. Now that we have all these numbers, I don't think we need the numbers anymore. So using z instead of t gives only, I have 3% error on each side, so my total error is 6%. That's a 94% confidence. Instead of 95% confidence. 30 years ago, you would say, well, who cares? Come on. I'm not going to make more tables than 30 for you to look through. 30 pages in a book where you have to flip through and find how many distributions you had to do. You know, depending on if you want a 95% or 97% or 99%, you need tables for all of these things. Right? That's 30 pages in a big fat book with all these calculations that someone sat there and did. Now we get them instantaneously with Google. 94% confidence, 95% confidence. Remember, this is catastrophic loss. This is this is Lehman Brothers. This is out of business. The difference between a 5% chance of going out of business and a 6% chance of going out of business is a 20% increase from 5 to 6, right? 1 out of 5 is 20% increase in going out of business. Catastrophic loss. People, when they didn't have computers and they couldn't just look this stuff up and compute immediately, they did this because what else are you going to do? There's no excuse for this today. The textbooks still say to do this. Please, 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 in the real world, those of you that are getting actuarial degrees, do not do this. Compute the actual numbers. It's very easy. You don't even have to be a programmer. You just Google it. Everything is, machines will do these calculations for you. Do not approximate a z, even if you have 100 degrees of freedom. It'll be extremely close, but it's the same keystrokes to get you 100 degrees of freedom as it is to get 29 degrees of freedom. Just do it. Okay? So, do not do this. Just use the true values, Dylan.
In the table I was looking at 1,000 degrees of freedom, it's still off by 0.01, I think. So.
Yep. Which 30 years ago you would say, come on, that's close enough. At a board meeting 30 years ago, you'd say, well, it's not really 95% confidence, it's 94% confidence, but come on. Everybody would say, yeah, you're right. Not today. Not with Amazon and these guys. They know when you're going to order the next bottle of shampoo to within a day. And they have it on a truck already. You haven't clicked the button yet. That's how these guys make the margins that they do. Everything is being optimized, and there's just no excuse for not doing it because it's so easy to do it. Okay? All right. I'm off my high horse. Let's talk about another. I'm not off my high horse. We're going to talk about some other types of things that need estimating. So this was just, you have a bunch of data, you want to know what the average is, you want to know a large confidence score for that average. Now, what very often happens, let's say you're testing two drugs, and you want to know which drug is better. Or you're testing, what's the example I have here? 2 light bulbs, okay? So new setting. Which brand is better? Okay, so you have brand A, and you have brand B. Assume again that the samples you're seeing are normal. You tested 40 light bulbs, 40 bulbs, and found among these 40 bulbs the average lifespan. You want to know, what makes a better light bulb? How long does it last? Let's say they pull the same amount of power, because that's also something you could be concerned about. The average lifespan, I'm just giving you some numbers so you feel comfortable with numbers. 418 hours. 418 hours. We could just make these numbers up. And then let's say you have 50 bulbs of, you're going to test 50 bulbs of brand B, and the average lifespan you saw there was 402 hours. So naively you would say, all right, brand A lasts longer than brand B. Done, we should buy brand A. As a statistician, you should say, wait a second, are we actually confident in this? What's a 95% confidence interval in the difference of their means? And if that confidence interval contains 0, then we don't know with 95% confidence that one is better than the other. Right? Is there actually significance in the difference between these? Are the numbers big enough to be able to conclude something like this? Okay? The first problem is we're going to assume that it's Gaussian, but lifespans are positive. All right, never mind. Maybe the mean is so large relative to the variance that we're not worried, negative lifespans of light bulbs have a microscopic, probability. So what are we going to do? So we're going to do 2 things. First of all, let's assume, again, there are 2 things. Let's pretend, for some ungodly reason, we know the variances, or we have guesses at what the variances are, and then we'll remove that assumption. Okay? So version 1, assume you know the variance of the 2 light bulbs, and for the first light bulb the variance is 26, and for the second light bulb the variance is 22. So already you can see 418 give or take 26, 402 give or take 22, those intervals intersect. Okay, but that's just something very crude. it's really how many light bulbs have you tested that's going to tell us whether or not these values are significant, whether there's difference. Okay? Does everybody follow? Dylan?
Is that variance or standard deviation?
Sorry, which one do I want? I have in mind, I mean, I'm just making up these numbers anyway, so, yeah, but this is the standard deviation. So, the square of that is the variance. All right. Okay, so if we know sigmas, and we're just trying to compute mu's, and actually we're just trying to compute the difference of two mu's, here's what you do. So I want to know intervals for the true mean. So this is the empirical mean, right? This is x bar A, and this is x bar B. The empirical, the sample mean for bulb brand A, sample mean for bulb brand B. I want to know the true, or an estimate, for the difference of the true brand A mean versus the true brand B mean. And I want to know not just the value, I want to know a confidence interval. I want to know, let's say, 95% confidence interval. Well, let's compare it to XA minus XB, right? My obvious guess is to take XA minus XB. So let's look at XA minus XB, X bar A minus X bar B, minus mu of A minus mu of B. What is this as a random variable if I'm assuming that my samples are Gaussian? So that's the big assumption. Big assumption. Assume light bulb lifespans are IID Gaussian. IID normal. They're not IID from brand to brand. There's one distribution for brand A, there's another distribution for brand B. Grant?
Why are we subtracting x bar B, mu A, and mu B, or is there a parentheses?
There's a parentheses. Thanks. Let me put the parentheses here too, just to emphasize. Right? The obvious estimate for this difference is this difference, and I want a confidence interval for this difference. Okay? So our assumption is the light bulb lifespans are IID Gaussian. So if I have the difference of, by the way, so what's the distribution of the sample mean? If the samples are Gaussian, then the sample mean is also Gaussian, right? And what about the distribution of negative a Gaussian? Well, when you subtract off its mean. So let's rewrite this. Here's the trick. The trick is that this is exactly the same thing as x bar minus mu A minus x bar minus mu B. That's the trick. And I hope you see that. X bar minus mu A minus x bar minus negative mu B. So this is a plus sign mu B, this is a plus sign mu B. This little bit of algebraic parentheses is the whole idea. Okay, you guys see this? So I want to estimate this in terms of this. When I rewrite it like this, now I have Gaussians that have mean 0. What's the law of the negative of a Gaussian of mean 0? Same law, right? Mean 0 means that we're centered at 0, and the Gaussian is symmetric around x goes to negative x. So this is also a Gaussian. This is a Gaussian. What's the sum of two Gaussians that are independent? Gaussian. So the sum of two independent Gaussians is Gaussian. This whole variable is Gaussian. Okay? So let's say that again. This is Gaussian mean 0. This is also Gaussian mean 0, which implies that this whole thing is also Gaussian mean 0. And the sum of two Gaussians, and that implies that this whole variable, I'm not going to give it a name just yet, but this whole variable is Gaussian. What's the mean? what's the mean of this thing? 0, right? This has mean 0, this has mean 0. I'm adding two mean 0 things. Gaussian mean 0. What's the variance? If I have two independent variables, the variances are the sum of the variances, right? If you have independent variables, the variance is sum. The variance of the sum is the sum. What's the variance of this variable? Sigma a squared over NA. The number of samples, NA is 40. The number of samples I had of type A. And what's the variance of this one? Other than Dylan? Sakina? Yeah, exactly. Same thing. Sigma b squared over NB. Okay? So that thing is a mean 0 with this variance. Gaussian random variable. So if I want a Gaussian normal random variable, that means I should take xa bar minus xb bar minus mu a minus mu b, that's the same thing as this, divided by the square root of its variance, sigma a squared over na plus sigma b squared over nb. And then the probability that this in absolute value is bounded by za over 2 is equal to 1 minus a. This is now a standard Gaussian normal, so I can use the cumulative Gaussian normal distribution to work out what confidence interval I get. I took this thing, it had mean 0 already. This was its variance. I divide by the square root of the variance. And that's a Gaussian normal, which means the probability of it lying in some interval is 1 minus alpha if I make that interval z alpha over 2. Same as before. Does that make sense? Any questions? Okay. So if you actually do these numbers, so okay, let's finish the punchline, which is how do I get an interval for this difference? I just multiply by this big factor, which implies with 1 minus alpha, well, I guess I should say times 100% confidence, mu a minus mu b lies between x bar a minus x bar b and x bar a minus x bar b minus something and plus something. The plus is whatever that number is, 1.96 or something, z alpha over 2 times that big square root. And this, I'll put the square root on this side, za squared over na plus sigma squared b over nb. Okay? This is the variance, this was the mean, and I have the same thing on the other side. That's the interval. If you actually put in, now we have all the numbers we need. X bar a is, do you remember what x bar a was? 418. X bar b is 402. So I'm going to put here 418, 402. Z, let's say we want 95%. So let's set alpha equal to 0.05. Z is 1.96. That's your 2 sigma, the hedge fund. What's sigma A? We were told the variance. What did I say? It was 26. Sigma B is 22. What's NA? How many were there of sample A? 40. How many were there of sample B? 50. I'll spare you the calculation. What you get is the interval I write it down. I was going to do the calculation, but let me not flip back and forth. So these are just numbers now. You put in the thing. I'm going to guess. I'm just going to guess. Let's get a rough, a very rough. Let's just pretend. I'm just going to pretend that this comes out to, just to follow the arithmetic. Let's say this means that this difference is between 3 and 6. So with 95% confidence interval, the interval of the difference is between 3 and 6. What do we conclude? Is brand A better?
Yeah.
Yes.
0.
Definitively better, because 0 is not between 3 and 6. If it came out to negative 3 and 6, then with 95% confidence, well, A looks better, but no, actually I don't know that there is a significant difference between them. And if B costs a lot less, go ahead and buy B. Right? That's what this kind of confidence interval analysis is teaching you. It looks from the means like it's better, but we had different values for the number of experiments that we ran. We had different variances. Again, this is all assuming we know the variance from some other, God gave us the variance. That gives us a confidence interval. So with 95% confidence, I can't say with 95% confidence that A is actually better than B, because 0 is in this range. So if B is cheaper, go ahead and buy B. It's not a big deal. If that 3 is a positive 3, then it's definitely better. And now you need to do an analysis of how much extra will it cost to run and replace the light bulbs because they die sooner, versus how much more expensive are light bulb A. Does that make sense? Any questions? Taylor. If it's between negative 3 and negative 1, so
That'd be very bad.
So it would in principle be bad for A, but if you look at it, it can't possibly be between negative 3 and negative 1, because this number is already positive, and then we're adding some positive amount and subtracting some positive amount. So whatever the interval is, its center is going to be positive. It's just a question of whether relative to, so here's 0. We know that the center is going to be positive. And the question is, with 95% confidence, do I have an interval like this, or do I have an interval like this? Does 0 get into that 95% confidence interval or not? But this computation can't come out where the interval is skewed to the other side of where the mean is. It looks like A is better. Any idiot will look at this and say, well, A had a longer lifespan. Let's buy A. You, the statisticians, the mathematical statisticians, should say, wait a second, do we really know that A is better, or is this not statistically significant to say that A is better? That's a light bulb. Or a drug. Does drug A actually help people more than drug B, when drug A costs $1 trillion and drug B costs 5? Right? This is real stuff. Now, the thing that's not real about this is knowing sigmas. So let's go back to what happens if you don't know sigmas. Any questions before we move on from this example?
Yeah.
Yeah.
Two random variables with the mean 0. If 0 can be added up to another Gaussian number, right?
You're saying the two variables. Let me put this slide back up, and then I'll get to Andrew's question. We have two variables. They're both Gaussian with mean 0.
Yeah. So they can add up to make out a new Gaussian.
And they're independent, so their sum is Gaussian. Yes?
If their mean is not 0, so they cannot add.
If their mean, so that's right. If the sum of two Gaussians, if they have the same mean, is a Gaussian of the same mean.
Yeah.
Andrew?
You say the subscript next to
The subscript next to Z here? This is Z alpha over 2. Same as before. I'm trying to capture a 95% confidence interval. I'll use z 0.025. 2.5%. Okay? And the same story for a one-sided constant. If you only care about the upper bound and not the absolute value, then you just put the upper bound z alpha with no absolute value. So that'll give you not a both sides, but if you only care about the upper bound, it'll give you an upper bound with more confidence because you're not trying to capture an extra condition. Okay? Actually, for this kind of example, the more interesting thing is all you actually care about is the lower bound, because the lower bound with large confidence is going to tell you whether the 0 is there or not. Right? For this kind of problem. Okay. So more realistically, we don't know sigma. Let's talk about that. This is page 3. More realistically, we don't know sigma. So what do you do? Well, so what do you do? So now you get to this xa bar minus xb bar minus mu a minus mu b. Let's start back at this equation. Bless you. So what do you do? So, I want to divide this one by its. So if I normalize this by its, let me say, try. If I normalize this by its SA squared over n, a, that'll give me a t distribution. This is t distribution with na minus 1 degrees. And this is the same thing, t distribution with nb minus 1 degrees, if I normalize it like that. But the difference of two t's is not a t. Well, it's complicated. So basically, there's not a simple formula, and I guess this really bothers me as I was reading over the textbook last night, thinking about how I'm going to explain this stuff to you guys. There's not a simple formula, so we're going to make an extra assumption. So there's no simple solution to no simple expression for the distribution of this, unless we make an extra assumption that sigma A is equal to sigma B. I don't like it, but you should know what to do in this case. Okay? Why is there no simple expression? You see, I'm going to want to divide this by this, and I'm going to want to divide that by something else, but then I'm not getting an estimate for mu A minus mu B. I'm getting an estimate for some weird linear combination of mu A and mu B, but not the actual difference. The only time when I get an expression for the actual difference is in this case. Let's see why that's the case. Do you remember why this is a t distribution? It's a t distribution because xa bar minus mu a divided by square root of sigma a squared, whatever sigma a is. This is Gaussian. And then we're going to multiply it by 1 over the square root of chi squared. So this is sa squared. Now I need to multiply by n minus 1 and divide by sigma squared. That's 1 over a Gaussian. That's 1 over a chi squared. So S squared over sigma squared times n minus 1 is chi squared with n minus 1 degrees of freedom. So this is 1 over y. I need to divide y by nu, the number of degrees of freedom, so I'll divide by n minus na minus 1. So that's this, and then I have to take the square root. And then I take the square root. So now I have a mean 0, variance 1 Gaussian times 1 over a chi squared with n degrees of freedom, with nu degrees of freedom. Right? That's what a t-distribution is. And these sigmas cancel out, and that's where this came from, right? The n minus 1s cancel out also. That n is an NA, and this n is an NA. So this n minus 1 cancels that n minus 1. That NA is still there. I'm just reminding you how we got to the t-distribution. Is everybody with me? Okay. So, but here's the miracle. If the distributions are the same, then this factor that I need to divide out by will be the same on both sides. And then when I multiply through, I'll get the right. So you'll see. Let's do a little bit of algebra. How do I want to set up this algebra? It's a little bit complicated. Let me say it like this. Let me say it like this. Let me say it like this. So I want this thing. This is the thing I'm trying to estimate. I'll write it again. xa bar minus mu a minus xb bar minus mu b. What I want to do, all right, let me just write the expression that I will get in the end. Here's the observation. Okay, here's the key observation. The observation is that if I take this thing, namely na minus 1 over sigma a squared sa squared, again, this is a chi squared with n minus 1 degrees of freedom, and I add to that nb minus 1 sb squared over sigma b squared. This is also a chi squared. It has nb minus 1 degrees of freedom. This is chi squared with na plus nb minus 1 degrees of freedom. Right? You see that? But that doesn't help us if the sigmas are different. If the sigmas are different, then what I want to do to get a Gaussian here is put sigma a, and what I want to do to get a Gaussian here is divide by sigma b. But if they happen to be the same, that's our big simplifying assumption, then the thing that you want to divide by, at least as far as the sigmas are concerned, is the same both here and here. So using the fact that the sigmas are equal, that assumption implies, so this variable is 1 over sigma squared, so I'm writing sigma for both sigma a and sigma b, times na minus 1 sa squared plus nb minus 1. I've pulled out the sigma squared, sb squared. So that is a na plus nb minus 2 degree of freedom chi squared. Okay? So this difference is still a Gaussian. This is still a Gaussian. This is a mean 0 Gaussian. Mean 0 Gaussian. And the variance is, here's the key, here's the miracle. What's the variance of this Gaussian? We already said. The variance of this one is sigma a squared over na, sigma a squared over na, plus sigma b squared over nb. And if we had different sigmas, we wouldn't be able to write this as just sigma squared times 1 over NA plus 1 over NB. This sigma squared has pulled out. This 1 over sigma squared has pulled out. These are independent with these. So now I can take a Gaussian and divide it by an independent chi-squared and get a t distribution. That's the miracle that happens when the variances happen to be the same. And if they're not the same, then there's no way of getting rid of these two sigmas. They don't add the same way that these sigmas in the denominator add. And so they don't cancel out, and so you get some complicated distribution that you don't know how to estimate. So the miracle that allowed us to replace, it's right here. The miracle that allowed us to drop the sigmas and just work with s's in going from a Gaussian to a t distribution is that sigmas cancel top and bottom. There's no more sigma. We don't know what sigma is, right? But the sigma just theoretically cancel out, and so we can just work with the sample variance instead of the true variance. But that just won't happen if your variance, if your true variance is a sum of the sigma squareds, and the thing that you want to divide out by is some of the reciprocals of the sigma squareds, then this miracle of them canceling out top and bottom doesn't happen. Justin?
Is this a safe assumption we can make normally? Or
No. Yes, this is an assumption that you can make in a textbook and have a chapter on. I mean, there's no reason whatsoever for the variances to be. One company is manufacturing in, I don't know, China, and another one's in Vietnam, and they have different, performance thresholds.
So then, if you're trying to solve industry problems, are there ways to make sure that your variances are the same? Like, we play around with your sample size?
So, if you're really trying, if this is a serious application, you're probably going to want to get approximate values from an unrelated experiment, get approximate values for sigma squared, and then use method 1. Pretend we know sigma squared. Because there's theoretically no way to get rid of this unknown sigma squared in this algebra. And so you don't know what the distribution is without knowing something about sigma squared. But if they're being made in the same factory that has the same kind of thresholds for mechanical errors, then maybe there's some reason you can make this assumption. All right, so the whole point I wanted to make is if you can make this assumption, then everything we said before works, because this 1 over sigma squared exactly cancels this positive sigma squared when we do this operation of renormalizing the Gaussians. So this is now our Gaussian. We're going to renormalize by this 1 over square root of that, and we'll multiply by this y squared divided by its degrees of freedom, and let's see what comes out of that. Okay? Is it clear what calculation we're about to do? We're just going to put everything together. So when you put everything together, here's what you see. I'm going to try to leave all of this here. This is page 4. So let's put everything together. So I have xa bar minus mu a minus xb bar minus mu b. That's my analog of, you can't see what it is the analog of. By the way, am I writing big enough? You guys in the back, can you see this? Okay. So that's my analog of this. So this turns into that divided by its variance, by the square root of its variance. That's the square root of sigma squared times 1 over NA plus 1 over NB. This is a Gaussian, mean 0, variance 1. I'm just copying this process. Then I want to multiply. Okay? So far so good? And we see where we got this from. I want to multiply that by a y squared, an independent y squared. Here's my independent y squared, but I want to put it in the denominator. So my independent y squared is a 1 over sigma squared times NA minus 1 SA squared plus NB minus 1 SB squared, which will be divided by the number of degrees of freedom. And the number of degrees of freedom, so dividing it in the denominator is the same as multiplying it upstairs, and the number of degrees of freedom is NA plus NB minus 2. And we would have a complicated mess with sigma A squared plus sigma B squared here, and 1 over sigma A squared plus 1 over sigma B squared, and they wouldn't fall out. But in this case, they exactly do. And everything that's left is calculatable from the data alone. The sample variance is just observed. You know how many observations you had. That's the ends. The ends are all completely known to you. These samples are, and the sample means are observed. So now you have an interval for mu A minus mu B just in terms of this data. Does that make sense? Does it make a little bit of sense? Does it make a lot of sense? Juliet, it makes sense? This stuff gets complicated. It's a lot of, at the moment it's just algebra. But hopefully the idea is clear. These sigma squareds wouldn't cancel if we didn't assume that they were the same. Well, let's assume that they're the same and see what we get. So what is our 1 minus alpha confidence interval? So 1 minus alpha confidence interval is that mu A minus mu B has an upper bound and a lower bound, minus something and plus the same thing. So what is it? This is what kind of variable is this? It's a t. I had a mean 0, variance 1 Gaussian. I divide it by a chi-squared with NA plus NB minus 2 degrees of freedom. So this is a t distribution with NA plus NB minus 2 degrees of freedom. So if I want to know that this number is at most t alpha over 2 with this many degrees of freedom, then that'll tell me what my 1 minus alpha confidence distribution is. In other words, I'm going to put some number here, and that number is going to be t alpha over 2, comma, the number of degrees of freedom is NA plus NB minus 2, times something very big. And that very big thing okay, so is it clear why this is the t? Because that's what this variable is, and I want to know when the absolute value of this thing is at most that. But I have all this other crap floating around, so all that crap just goes in here. But it's just a calculation. It's just algebra. Okay? So I'm moving this to the other side. So I have a factor of NA minus 1 SA squared plus NB minus 1 SB squared divided by NA plus NB minus 2 times 1 over NA plus 1 over NB. That's the crap that comes out of the algebra when you move everything from here to the other side of the estimate. It's not pretty, but it's algebra 1. I mean, we can do this. We're just manipulating some algebraic expression. And I want the square root. And I want the square root of this. I want the square root of that, because it was square rooted here. All right. Are we happy with this? This has a name, by the way. This thing is called the pooled estimator.
With the square root of the square root.
Without the square root.
Okay.
So it's a pooled, in other words, it's saying if I have a sample variance, what this is saying is what's the sample variance when you pool both experiments together? Right? You know, pool, like, you know where billiards, the word billiards comes from. You guys know? From horse racing. When you're horse racing, everybody's placing bets, so you pool all your bets, and what do you do while you wait for the horses to run? You play a game of billiards. That's why billiards is called pool. Okay, so pool is what happens when lots of experiments are happening at the same time. You have a whole bunch of lotteries happening simultaneously. Let's pool them together. How should we pool them together? How do we combine these variances? This is how you combine the variances. You take the A variance, multiply it by the number of experiments minus 1. You take the B variance, multiply it by the number of experiments minus 1, and you divide by this. So this is the correct normalizing factor for how much you should weigh. I mean, notice that this ratio plus this ratio adds up to 1. So this is a convex combination of SA squared and SB squared, which is like the sample variance when you pool both experiments, if they have the same variance, true variance. Okay? Does that make sense? I said that too fast? Should I say it again? No. How many are with me? Who's following along? Okay, great. This makes sense. All right. Do I have time for one more? I think I do. Okay. This is an important one. Let's talk about elections. So again, the punchline is, if you don't know what the sample variances are, but for some reason if you don't know what the sample variances are, you can't do this, basically, numerically. I mean, you can do things numerically, or you should do something to guess what the sample variances are and use the first method. If there's some reason that you think the true variances, I said sample variances, if you think the true variances are the same, then you can use the t-test. Let's talk about elections. So this you read in the newspaper every day. I'm sure today there's an article in the paper that says we have a 95% confidence interval that says people prefer candidate X to Y. Or let me give you a specific one. So here's an election. Yeah, let's make it not political. So vaccines, flu vaccines. So example, here's a question. 400 people got a flu vaccine. And 136 of them had some kind of reaction. A rash, I don't know, discomfort. The rest, the other 200, and I'm doing math in public, 264 of them were like, yep, flu shot, I'm good, I'm out of here. But 136 of them said, this is uncomfortable. You would like to understand. So what is that? Whether or not you get a reaction is a 0 or 1 variable. That's a, what was it? Bernoulli, yep. So each xi is 0 or 1, whether you had a reaction or not. Had reaction. This is a Bernoulli trial. It's a coin flip, but of course it's a weighted coin flip. This is so the probability that xi is equal to 1 is some parameter theta that we don't know. What's an estimator for theta? What do you think is the probability? What do you think is the most likely value for theta? Either from the moment method or from the maximum likelihood method, you'll get the same answer. Other than Ernest? Andrew? X bar, yes. And what is X bar in our case? Well, it depends on what you mean by X bar. If X bar is you add them all up and divide by how many there were, then you got 136 ones, the rest were zeros, and then you divide by how many there were. So you're absolutely right, X bar is the estimator, and X bar in this case is 136 over 400. Right? Which is the expected value. So theta, this is just using the fact that theta is the expected value of each xi. All right, so we think that this is theta. That's our best guess for theta. How about a confidence interval for theta? Okay. What about 1 minus alpha confidence interval for theta? In other words, I want to say what is x bar minus theta. I want to try to get some probability density for x bar minus theta. Now, what is x bar minus theta? What is x bar? X bar is a sum of Bernoullis. X bar is a sum of xi, 1 over n. These are Bernoullis. What's the sum of Bernoullis? Does everybody remember that? Binomial distribution? This is why on week 1, we spent reviewing probability so that this stuff was fresh in your head. Of course, it's been 6 weeks since then. But so x bar, when you average a bunch of Bernoullis, you get a binomial. Binomial random variable. So I would like to understand this difference. Let's play around with that binomial random variable for a second. So recall that the probability that a binomial random variable, namely x bar, the probability that this is equal to k is equal to, what is the distribution, the density function for this discrete random variable? Yep, n choose k. N is the 400, exactly. So the probability that it's equal to any k is 400 choose k. Theta, you had k successes, that's theta. I mean, if getting a rash is a success. Ernest?
If you're multiplying 1 over n by a binomial, it's still a binomial.
Oh, sorry. How do I want to say this? I want the sum. Yeah, let's call this nx bar. Nx bar. Nx bar is the 136. Okay, so the 136 is what's the probability that I had 136? You're absolutely right. So if I sum all those variables, what's the probability that I saw 136? Well, it's n over k, theta to the k. I had that many successes. 1 minus theta to the n minus k. That's the probability of each failure, and I had that many failures. You remember this? Everybody remembers binomial distribution? You add up, you don't average, you just add up a bunch of Bernoullis, that's a binomial, which is n times x. Okay, so that's a Bernoulli. What's the variance of a Bernoulli? I'm sorry, what's the variance of a binomial for which we need to know what the variance of a Bernoulli is? Okay, so you guys, if you don't know this, just redo this calculation. It's very fast. The variance of each xi is theta times 1 minus theta. Because this is, I mean, it's kind of trivial. This is theta minus theta squared. The expected value of x squared is theta, because it only happens when x is 1 with probability theta. And the expected value of x is also theta. So I just proved to you. If you didn't remember, then you could derive it in 1 second. Okay, that's the variance of one of them. So what's the variance of x bar?
400.
This divided by n. So that's this divided by n. But of course, it's not x bar that I want. It's n x bar that I want. So what's the variance of n x bar? That's the binomial, the sum. Yep. So it's n squared times this. So it's n times theta times 1 minus theta. Okay? And now let's go back to our calculation here. So I have nx bar minus n theta. So nx bar is my binomial. Minus n theta, that's the expected value of the binomial. Divided by the variance, by the square root of the variance of my binomial, n times theta 1 minus theta. This is asymptotically, for large values of n, normal. Okay? So this is normalized. This is the fact that the binomial, I mean, it's true for any distribution, but de Moivre-Laplace was the first instance of the central limit theorem that the binomial goes to Gaussian. This is the central limit theorem. Actually, de Moivre Laplace. De Moivre Laplace. Okay? So this is approximately Gaussian for large values of n. This is approximately Gaussian with mean 0, norm 1. And so I can get an asymptotic estimate for it. So approximately, now we're losing a lot of precision. A 1 minus 95% confidence interval would be, slide this up. What would be my confidence interval, 1 minus alpha confidence interval, is that the probability of n x bar minus n theta, but let me pull out the n, divided by root n theta 1 minus theta in absolute value is less than z alpha over 2. Well, it's not really 1 minus alpha. It's not really 1 minus alpha because I'm pretending that this thing really is a Gaussian. It's not. It's a normalized binomial. So what should you really do? You should take a true binomial and do this. Except we don't know theta. Right? That's the main problem here is we don't know theta. So it looks like, so where's my interval? What's my interval? It turns out that you can literally solve for theta. The algebra is sufficiently simple. Well, let me write it like this. Let me simplify this. So this is some algebra. X bar minus theta is, in other words, theta is between x bar plus and x bar minus z alpha over 2 times, so what do I have here? I have a root theta times 1 minus theta times root n divided by n, so divided by root n. Again, that's just algebra. Okay? What's the problem with this as an estimate for an interval for theta? It's in terms of theta. Oops. Okay, so there are two things you're going to do. The first, did I leave this as an exercise? Yes, I did. I left it as an exercise. So there's a homework problem that you can solve the algebra. This is simple enough algebra that you can solve this and turn this into an actual interval for theta. So the thing one that you can do, so not really, is I still have theta here. Okay, so tweak one, which is homework, solve for theta, solve the algebra for an interval in theta, for a true interval in theta. That's the less lazy tweak. The lazier tweak well, do I have a guess for what theta is? X bar. So do a further approximation. Further approximation is that these thetas I'll replace by x bar. And so now I have the interval that theta differs from x bar by at most z, and this is really rough, square root of x bar times 1 minus x bar over n. Okay? So this is like the crudest thing you could do. And, okay, we're going to get to the difference of Bernoulli's next time.